Hello everyone and welcome to another class of ATMO 620. I hope you're all doing well. Today we are still talking about gases and thermodynamics. And in particular, today we will talk about quote-unquote moist thermodynamics. So what do I mean by that? Well, the last few classes we talked about, just to remind you, ideal gas law, first and second principle thermodynamics. All these were sort of under the assumption that we were dealing with a very simple gas that was made of just one single substance, nitrogen, oxygen, and whatnot. And in few instances, we specified that we were actually dealing with a dry parcel. You remember when we said that infinitesimal changes in specific entropy were related to changes in, I'll write it log again, and the logarithm of potential temperature. Remember that? Well, excuse me, I think this was CP. That was done in the simple ideal case of a dry parcel. But we're all very familiar with the fact that parcels in the atmosphere are not dry at all, and they contain water vapor. Sometimes they don't contain a whole lot of water vapor. If you're in the Sahara Desert, maybe that's not a whole lot of water vapor and not a lot that you have to worry about. But by and large, oceans cover 75% of the planet, and so you should expect a lot of water vapor in many parts of the world. The tropics cover 50% of the planet, and there's a lot of water vapor in the tropics, in case you haven't noticed yet. So what happens when you include water vapor in your equations? Okay, well, let's start. And let's start simple. First of all, air is an ideal gas. It's a mixture of gases. Oxygen has something like 25%. Nitrogen is about 25% or so. And then there are other gases that are less abundant, among which water vapor, CO2, argon, and whatnot, and other gases. But the air is an ideal gas. And for air, we said, well, this very simple law holds true. PV equals nRT, or another way to write it was P equals rho RT, where this was the R of dry air, which I hope by now everyone has learned or remembers. RD is approximately 287 joules or joules per kilogram per Kelvin. Okay, but so how does water vapor work? Well, the same thing holds for water vapor, okay? If you had a box that only contained water vapor, then the pressure would be given by something similar. It would be, let's say that this is pressure of dry air, this is rho of dry air. Well, in that box, you'd have pressure of the vapor equals rho of the vapor, R of the vapor times temperature. P of the vapor, for historic reasons, is denoted typically by E. Don't ask me why. But that's how we're going to denote it from now on. Okay. Suppose you have the box with water vapor. That's how you determine the pressure in the box. What if you had a mixture of water vapor and dry air? What would be the total pressure? Well, I hope you remember Dalton's principle or Dalton's law. It would simply be the sum of the two pressures, the dry air and the pressure due to the water vapor. Okay? Anyway, this is the ideal gas law for water vapor. Okay? And in this case, the gas constant, RV, is different from RD. And RV is actually 461 joules per kilogram. Okay? So please keep this in mind. This is something that people get often wrong. Gas constant of dry air, different from gas constant of water vapor. Reason? Well, the molecules are different, okay? dry air, let's say the dry air is just, well, okay. Let's say the dry air is mostly nitrogen and oxygen. These are diatomic molecules that only, well, as the name suggests, contain 2 atoms. Water vapor is H2O that has very different weight and just different properties, okay? And so it's reasonable that the gas constant is different. Please keep this in mind. Actually, the ratio between the gas constants of dry air and water vapor, as you can imagine, it shows up a lot in the various equations, and it's typically denoted by epsilon, okay? We'll see it down here. Epsilon, which I write like that, is the ratio between dry air and water vapor gas constant. It's something of the order of 0.6 if you compute it, okay? Okay, so suppose now, now let's think about the atmosphere. There is almost no place on Earth where water vapor is 100% of what's out there, right? Dry air is always going to be the dominating effect, the dominating gas, right, in your mixture. There is going to be water vapor, and the changes due to water vapor are going to be tremendous and dramatic for the atmosphere. But water vapor is not. It's always going to be a tiny fraction of the total gas that we're dealing with, okay? Okay, but how much water vapor is there? How can we denote how much water vapor is there? Well, we have a few ways to define the quantity to quantify the amount of water vapor present. The first is through a quantity called mixing ratio. And mixing ratio is simply the density of water vapor to the density of dry air. Notice that I'm using density, not mass, okay? Density. Just use the ideal gas law, okay? And density of water vapor over, I'll just do it here. Density of water vapor over density of dry air. I hope you don't mind that slides get super busy with my writings. I hope it's not too confusing. Now, use this gas law for water vapor. This is just E over RVT. This is an R. Divided by, we do the same thing for dry air. This is P dry air over dry air T. Now, temperature simplifies because it's the denominator of both terms. And so this is RV over RD. It's 1 over RV over 1 over RD, which shouldn't take much for you to realize that this is RD over RV, which we define here as epsilon, E over PD, which kind of makes sense. It's a gas. They're at the same temperature because it's a mixture, and so it makes sense that they're all at the same temperature. Let's say that the mixture is well homogenized, okay? And so the mixing ratio, the amount of the water vapor is proportional to the differences in pressure, to the fractions of the pressures. We don't know how much PD is, right? Or we don't know how to express it. We don't care for it, but we also know Dalton's law, which is over here, and it says that PD is P minus E. So this we can always rewrite as E divided by P minus E. Okay, this is a way to relate the mixing ratio to the partial pressure of water vapor and the total atmospheric pressure. Okay, this is convenient because there will be times in your life when you will know the partial pressure, but you will not know the mixing ratio, and you'll need the mixing ratio, or vice versa. Maybe you have the mixing ratio, but you need the partial pressure. Okay, so that's where that comes about. Another way to define, to quantify the amount of water vapor present is through specific humidity. Specific humidity is defined as the ratio between the density of water vapor, divided by the sum of the density of the dry air and the density of water vapor. Okay? it shouldn't take much for you to realize that this is a close cousin of the mixing ratio. In particular, if you divide both numerator and denominator by the density of dry air, then this is rho v over rho d. Becomes r. Rho d over rho d is 1, and same rho v over rho d is r. Okay, so Q and R are actually very closely related. Just as an FYI, I hope we're all on the same page with this. We're all aware that, given that we're talking about the changes that water vapor gives to a parcel of air, we're all aware that water vapor is lighter than dry air, right? This may be counterintuitive, but we can write it here. Water, actually let me write it in cursive so that everybody can get confused. Water vapor is heavier than air. Exclamation mark, because this is a very counterintuitive thing. And if you don't know it, it takes a while to think about it. But if you think about the molecular structure of these two gases, then it kind of makes sense, because nitrogen has atomic weight of, 14? And oxygen is 16, I think. And so the molecular weight of this is 28, and this is 32. Molecular weight of the vast majority is nitrogen, and so we can say that the molecular weight of air is 28. Molecular weight of water, 16 plus 2 is 18. Okay? So dry air is almost twice as heavy as water vapor. Actually, if you take 18 over 28, the ratio is, I think it's about 0.6, which is also this 0.6, but I guarantee you that this is pure coincidence, and it's got nothing to do with these values. Anyway, okay, so this is just an FYI, and this will become important later when we'll talk about buoyancy and why air goes up. In the tropics, a lot of the times air goes up because it's humid and not because it's hot. Okay, so humidity can actually be pretty important in promoting buoyancy and ascent. One quantity that is related to the partial pressure and to the presence of water vapor is what we call relative humidity. Specific humidity here was defined as a ratio of densities. Relative humidity is defined as a ratio between two partial pressures. One is the partial pressure of water vapor, and this E star is what we call saturation vapor pressure. What is this, and what does this mean? Well, I think you're all pretty familiar with relative humidity. This is what in common life, this is what we call humidity. Oh, look, it feels so humid today. Well, water vapor molecules are typically, water vapor is typically dissolved in the air, if you will. You know, the same way that sugar is dissolved into water when you mix it, right? When you're having your coffee or you want to boil pasta and you put salt in the water because, my dear American friends, you do put salt in the water when you want to make pasta. And you'll see that the salts typically, or the sugar, will dissolve in the water or in the coffee or in whatever liquid. For water vapor, it's essentially the same thing. Okay, and water vapor is kind of dissolved. But if you were to keep adding water vapor, much like if you were to keep adding sugar in the water, at some point the water will not be able to withhold sugar anymore. At some point, dry air molecules cannot withhold water vapor, cannot keep having, they're surrounded by too much water vapor, if you will. And so what the atmosphere does, it gets rid of the additional water vapor. Water vapor is not dissolved anymore. You could try this at home, but maybe you shouldn't. I don't know. But one simple experiment to see to see saturation, to see what happens when you pass the threshold of saturation and you have what is known as supersaturation, which we will talk about extensively in the second part of the class. We'll talk about microphysics. Is if you start adding sugar to water, at some point you will not be able to add sugar anymore. If you heat up water will be able to withhold a little bit more of the sugar, because the amount of substance that you can dissolve is dependent upon the temperature. Same goes with water vapor and temperature, right? But and so you warm up the water, you put it in a pot and you heat it up. You start mixing more sugar, and then you cool it down and you make it cool really quickly. If you were to insert a stick in the heated water, please don't insert your finger or any part of your body. But if you were to insert a stick and let it there for a little bit, you'd notice that sugar would begin to crystallize on the stick. So the liquid suddenly sees an opportunity to get rid of the extra sugar and just dumps it all on the stick. And the atmosphere does something similar. We'll see the details in the next few classes. But for now, a measure of how much you can dissolve at a given pressure and temperature is given by the so-called relative humidity, which is defined in this way. It's a common misconception that relative humidity is defined in terms of the amount of the gas, in terms of mixing ratios, for example. But that's not true. Relative humidity is defined in terms of the pressure and the partial pressure of the gas. This is almost equal to our mixing ratio over the saturation mixing ratio, but it's not exactly equal. Okay, so just keep this in mind. Whenever you have to compute relative humidity, it's partial pressures, not mixing ratios. Okay, let's start talking a little bit more about this partial pressure, because I introduced, let me write it up here, I introduced relative humidity, and I said, well, that's E over E star. Well, this you can very simply measure in one way or another. But how about this? What is this stuff? Like, how do we know how much is E star? Meaning, how can we compute the maximum amount of water vapor that we can quote unquote dissolve in dry air? By the way, in the previous slide, I introduced R star, right? And you remember that R was also related to the partial pressure. So if you're asking how much is the saturation mixing ratio, well, that's simply this. Okay? So nothing too complicated. That's the maximum amount of the biggest mixing ratio that you can dissolve before you saturate. But let's stick to pressure, which is kind of simpler to think about. Okay, to compute this quantity, we can use some simple thermodynamic arguments. And by the way, in case you're asking, why do I need to bother, why do I care about E star? Well, you should care about E star because, and particularly about how E star is related to environmental variables such as temperature. Because you may be aware that there's this thing going on called global warming, whereby we are increasing the global temperature of our planet, right? And you'd say, oh, okay, yeah, but we're only increasing it by 1 degree. Well, 1 degree is a lot. And it makes sense to ask, if you're warming up the atmosphere, what's going to happen? Many things are going to happen. There are going to be dynamical changes. The glaciers are going to melt and polar bears are going to look really sad. But one thing that is going to happen at the thermodynamical level, and you can see right away, is that E star, the amount of water vapor that you can dissolve in the air, is also going to change. You're going to evaporate more water, that's for sure, because the oceans are going to be warmer, and so more water molecules are going to want to just bounce off and start dancing in the atmosphere. But you're also going to affect how much water vapor you're going to be able to dissolve, and that in turn will influence how much precipitation you're going to have on average on your planet. And so, don't discard this quantity just like, yeah, whatever. This is something actually very important that we need to understand and to keep in mind. Okay, in order to understand how this variable is related to other thermodynamic variables, let us consider a very simple system. Let's take a box like this one, completely closed. Let's say that initially it's the vacuum inside here. There's absolutely nothing, okay? And we're just going to put in some water, some liquid water. Let's say that this is at some temperature. Well, actually, when it's completely empty, it's at no temperature because there's nothing to define a temperature. We're just going to put in some water, okay? And what's going to happen? Well, you remember that we talked about the Maxwell-Boltzmann distribution of velocities in a gas, and I gave you a nice formula. Well, in a liquid, things will be more complicated because the interactions are not as simple as in a gas, but you can imagine that velocities in this gas and energies in this liquid will also be distributed with some kind of distribution. Some of these molecules will have more energy than others. And so some of the molecules from inside here, they'll have enough energy to jump out of the water like dolphins, but actually stay outside and start floating around like gas molecules. And slowly, this will, the internal part of your box, which is an awkward way to say it, but your box will become fill very slowly. It will start seeing some of these molecules. And look, some of these molecules maybe collide with each other. They form a heavier molecule, and the heavier molecule has lower momentum, maybe lower energy, because some was lost maybe in the collision. And so this will jump back in. Okay, so some molecules will jump out, some molecules will jump back in. At some point, eventually, if you wait long enough, you'll reach some kind of equilibrium. It will be a statistical equilibrium, meaning that it's not like molecules will stop moving, but the way that things change will remain constant. Which again is a funny way. It sounds like an oxymoron, but it's actually not. And what I mean by this is that the flux of molecules from the liquid to the gas will equal the flux of molecules from the gas to the liquid. That will be your equilibrium. Now, the space above the liquid in here, when that starts happening, when molecules collide, etc., when you reach equilibrium, the gas above here will be at saturation, okay? And the partial pressure at that point, at saturation, is what we denoted as E star, okay? And in this case, it only depends on the temperature of the gas. It cannot depend on anything else because there isn't anything else, okay? So how is this functional dependency? What does it look like? Okay. Well, we can use a little bit of math. And in particular, I hope you remember that last time we talked about Gibbs energy. And maybe you were asking, why are we talking about Gibbs energy? Well, we're talking about Gibbs energy precisely because of this. Gibbs energy during phase transitions, which is what happens when you go from liquid to gas or vice versa, does not change. Okay, so the Gibbs energy in your system remains constant. When you reach equilibrium, remains constant. At the same time, however, the changes in Gibbs energy, these are given by changes in Gibbs energy due to molecules that go from liquid to gas and changes that go from gas to liquid, from vapor to liquid. This will be changes in mass because some will eventually collide and they will have some specific Gibbs energy, plus changes in the mass of the gas because these evaporate and these collide. Gibbs energy of the gas. Okay, this will have to be 0. Okay, at equilibrium, the number of molecules that jump at a given time, that jump from liquid to gas, and those that jump from gas to liquid are exactly equal and opposite. Okay, so these two terms kind of cancel out, and what you end up having is that, because we just said dml equals minus dmg, you have that GL, the specific Gibbs energy of the liquid, equals the specific Gibbs energy of the gas. Okay? Excellent. Well, very good. We also remember that Gibbs energy had, if you remember, it had a differential form. Specific Gibbs energy could be written like this: specific entropy, dt, plus small v dp. What is small p, you may ask? Well, remember how we said specific entropy was entropy divided by the mass? Well, we can also define, given a volume of something, we can define a quantity called specific volume as the volume divided by the mass. Does this ratio look familiar? Well, of course, this is 1 over rho, 1 over the density. Okay, so specific volume is just the inverse of the density, but it kind of looks nice to use specific volume. So we can think about infinitesimal changes of Gibbs energy in the liquid and the gas phase, and these will be written in this way. Okay, now this term actually isn't very big now, is it? And we'll ignore it. Why is it not big? Well, remember we're talking about water, right? And so we're comparing two different terms. Actually, let me wait one more step before I say this, so otherwise it would sound. Otherwise, it's not entirely obvious why we should ignore that. So let's keep it for a moment. Anyway, we have this equivalence between these two terms. And what do we need from this? Well, this dp, remember that P in this case is the partial, well, it's not the partial, it's the pressure of the vapor, so it's E, and remember that we're at saturation, so this dp is really dE star. So this is exactly what we need. So take all the terms, all the P terms on one side, all the T terms on the other side, and you end up with an equivalence like this. dE star over dt is the difference in specific entropies over the difference in specific volumes. Okay, now is the simplification. Specific volume of gas and minus specific volume of liquid. This is what I see over here. This is the inverse of the densities, right? So this is the inverse of the density of air, inverse of density of water. What is the density of a parcel of well, this would be water vapor, but density would be of the order of 1 kilogram per meter cube. It's not exactly that, but that would be the order of magnitude. Okay, that we'll be thinking about. Density of the liquid, that is of the order of 1,000 kilogram per meter cube. So this is much bigger than that, which means that if we take the inverse, this is a lot smaller than that, and so this we can ignore. And so the changes of E star in dt are given by differences in specific entropy over specific volume of the gas. Okay, excellent. But, okay, can we say something more? Well, yeah, because the specific volume of a gas is related to the ideal gas law. So PV equal mRT. Remember, we're talking about the vapor here, right? So this is E, and particularly this is E star. And so you'd have that 1 over V. Sorry. Let me write this. You'd have that V over M. Okay, V over M would be RV times T divided by E star. Okay. And the other quantity, the difference in specific entropies, that is actually related to the change of heat while we're converting a unit of mass to vapor, okay, divided by the temperature. So remember ds dq over t, right? So change in entropy, if you want, we're talking about specific entropy. So specific entropy, changes in specific entropy related to changes in specific heat. Can we define specific? Well, of course we can define specific heat over T. How much is going to be the specific heat in this case? Well, when you're evaporating something or condensing something, how much is the heat that you're exchanging? Well, that's exactly the latent heat. That's what latent heat is for, because when you're at a point of phase transition, you're not changing temperature or whatnot. You're taking energy to break bonds between molecules, or vice versa. The bonds are going to cause molecules to give up some energy, and that is the latent heat energy. Well, that is latent heat. So that is the latent heat divided by T. So put all these things together, and you have obtained this equation that you're likely going to remember for a long time now. D star over dt equals LE star over RT squared. Okay? This is the latent heat of vaporization, and this is RV. Okay, be careful. 461 joules per kilogram per Kelvin, not 287 joules per kilogram per Kelvin. This equation is actually not particularly complicated because it's perfectly separable. D star over E star equals 2L over RV T squared dt. And you can integrate both these terms, and you'd have logarithm of E star equals to minus L RVT plus some constants, okay, that you can determine. And how do you determine the constants? Well, typically, one brings the system at zero, at freezing temperature, 0 Celsius degrees, so 273.15 Kelvin, and measures this, what the relationship is like, and then determines the constant in that way. So you plug it all back in, and you have this exact equation for how the saturation vapor pressure changes with temperature. This equation here, I failed to say this. This is called the Clausius-Clapeyron equation. Okay, and it's very important. There are, of course, approximate ways to write down that equation. You can plug in all the values, and this is what you get. Sort of more, it looks kind of empirical, but it's just like that instead of T0, E star 0, you just replace the actual values, and this is what it looks like. Notice also that something similar also holds for ice. Wait a minute, what does that mean? Well, it could be that when you are, so normally at above freezing temperatures, the saturation vapor pressure over ice is higher than saturation vapor pressure over water. And so when the atmosphere wants to condense stuff, wants to get rid of stuff, it's not really convenient to get rid of it through ice crystals, okay? And it just dumps it on cloud droplets. But below freezing temperatures, because of the values that we found in here, it actually happens that the saturation vapor pressure over ice is lower than the saturation vapor pressure over water, which means that it's actually, at some point, it's actually more convenient to create ice crystals than to condense liquid water. And that is interesting because if you had a box with some liquid water here, some ice cubes suspended for whatever reason, and water vapor molecules, well, you're still going to have some molecules of liquid that are going to come out and some are going to come back in. But you also have that for T lower than 273.15 Kelvin, these guys are going to grow. And so they're going to grow essentially to the expanse of liquid water. Okay, because you're always gonna have fluxes of molecules outside, but these guys are gonna keep growing because you're supersaturated with respect to ice before you're supersaturated with respect to water. Now this might seem like a really awkward system, and you might think, well, when are we ever gonna have something like this in nature? Well, you could have so-called mixed phase clouds. Mixed phase clouds. Some examples, thunderstorms. Now I'm going to draw a thunderstorm. Ready? So this is the thunderstorm cloud, and this is the anvil of the thunderstorm. Well, better than I thought, actually. So above something like 5 kilometers, give or take. Above here, you're starting to have ice. Above 10 kilometers, well, ice is going to be all that you have. So these are all ice crystals. Okay? More or less, just please don't be too picky. Below 5 kilometers, well, it's kind of warm, and so you're going to have liquid droplets. Between these two, well, you're going to have a mixed phase. You're going to have both. Another example are so-called Arctic mixed phase clouds. Which are kind of a real mystery because typically in the mid-latitudes, mixed phase stratiform clouds don't live much because there is a mechanism that we'll talk about called Bergeron-Findeisen mechanism. Bergeron-Findeisen. And usually there's also another guy, but I always forget the name. Bergeron-Findeisen is sort of the most famous name. This is a mechanism whereby ice crystals grow to the expense of liquid water droplets, super cool liquid water droplets. And essentially, when this mechanism kicks in, mixed phase stratiform clouds can glaciate in a matter of a few hours. Okay? So it's kind of an unstable state. However, Arctic mixed phase clouds have been observed to remain in the mixed phase state for days. And it's still not quite clear why that is. It's still kind of a mystery. And again, why is that relevant? Well, because liquid water and ice crystals, and we'll talk about this, interact with radiation very differently. And so they have a very different impact on the radiative budget at the surface, for example. And so why those clouds exist and why mixed phases continue to exist, it's kind of relevant if we are to understand, particularly in the Arctic, which is such a sensitive region where, having clouds and not having clouds and having them that trap latent heat fluxes, long wave heat fluxes, or others that reflect short wave heat fluxes. Well, it can make a lot of difference to radiative budget of the Arctic. So it's kind of important. Anyway. Okay, so that was a very important point, a very important equation that I hope you will all remember from now on. Now, for the remainder of the class, I just wanted to introduce a few more variables that may be useful in your life, and also some caveats on how to compute things. Because if you remember before, when we talked about just one dry parcel of air. If you remember, we said that we had a simple relationship between the heat and the temperature of the gas, right? In particular, changes in heat were related to mass that we're dealing with times the specific heat constant volume times changes in temperature, right? That's excellent. We can actually redefine this as changes in specific heat. And this is just that. Changes in temperature. Okay, very good. But that was with one gas. So, if this was dry air, this would be delta Q equals CV of dry air times delta T. Okay? What happens if we have water vapor as well? Is CVD different from CVV? Question? Well, the answer is, as you could imagine, yes. Otherwise, we'll be done for the day. And how do we determine how things change? Well, things will change quite simply. And because you could just imagine that, we can start from something like this. This would be delta Q will be given by mv plus md time the changes in the specific heat, okay? And this will be related to, changes due to the dry air, CVD, delta T, plus MV CVV delta T. Now we can collect the delta T, and this becomes MD CVD plus MV CVV delta T. Okay. If we divide everything by the total mass, then we would have the delta Q is MD CVD plus MV. Excuse me, I didn't write it very well. mv CVV divided by md plus mv delta T. This, let me rewrite it. We could also write it simply as a CV prime delta T. What is CV prime? Well, CV prime is the quote unquote effective specific heat capacity at constant volume, of course. Okay. So this is something that will be true from now on, that you can always rewrite, you can always define some kind of an effective gas constant for dry air, effective heat capacities or specific heat capacities for, sorry, not for dry air, for the moist air. And that is always going to be a combination of the specific heat capacities or the gas constants of dry air and of water vapor. Okay. Equivalently, if you divide by the volume, you can also define it in terms of mixing ratios, because sometimes that's simpler. Okay. This, I believe, is a typo. Yeah. So effective heat capacity would be a way to define it. Now you can also redefine the same. You can do the same exercise for heat capacity at constant pressure. Okay, and something similar would hold true. And by the way, why did we get to that stage? Well, let me write this this somewhere here on a new slide. So set 1 plus R. I think it's CVV over CVD over 1 plus R times CVD. Let me check. Yes, excellent. Okay. As a simple way to check that I did everything right, if you put R equals 0, there's no more water vapor, so it's only dry air, and CV prime equals to CVD, as it should. How could we simplify this? I hope you remember when we talked about Taylor expansions, that 1 over 1 plus x is 1 minus x, provided that x is really, really small. Okay. Is this true? Well, typical values for R in the tropics next to the surface, I would say something about 15 grams of water vapor per kilogram of dry air, which means 0.015 kilogram of water vapor over per kilogram of dry air. That's how much water vapor you have typically in the tropics. I think that the saturation mixing ratio, I'm going by memory, it should be about 22 gram per kilogram. So I think that would be about 70% relative humidity. And when I say tropics, I mean something closer to the equator than Hawaii. Here the temperature is a bit colder. Anyway. And so, yeah, R is a percent. So R, usually it's a good approximation to say that that's much smaller than 0. And so you have 1 plus R CVV over CVD, okay, times 1 minus R, right? Because 1 times CVD. 1 over 1 plus R has become simply 1 minus R. And this is CVD times 1. Let's collect all the terms that have an R. And these would be CVV over CVD. There's a 1 here, but it has a minus in front. And then there's minus R squared CVV over CVD. Now notice that this is a percent, and we're approximated essentially. We're saying that R is much smaller than 1. So we're happy with errors of a percent in this case, right? We're saying, yeah, everything regardless of percent like errors. So R is of the order of 10 to the minus 2 kilograms per kilograms. Let's not forget the units. How much is R squared going to be like? Well, square this, and that's 10 to the minus 4, right? If you were happy with an error of a percent, an error of a 0.01%, you shouldn't even take this into account. Okay, so this we can neglect. That's usually the trick. And we have a simple formulation: CVD 1 plus R CVV over CVD minus 1. And that's the approximate formula, and that's what I have here. Okay. You can compute how much this is, and you can plug in the numbers. And actually, let me give you the numbers here. Sorry, this I had not anticipated of doing, and so I have to find the books. Why did I not think of doing this beforehand? Well, that's just, one of those big mysteries. Okay, found it. CVD, these you can find tabulated, is about 719 joules per kilogram per Kelvin. Please always remember to specify the units because we're not mathematicians and units are important. CVV, as you probably guessed by the final result here, it's about twice as much, and it's 1410 joules per kilogram per Kelvin. Okay. Something similar holds for CPD, and a similar formula. You can do a similar formula using a sort of a similar process as I've done earlier. I think you could do it with enthalpy instead of heat, and instead of with specific heat, you could use specific enthalpy. I think it should work the same. And just giving you some numbers, CPD, this you will remember for a long time, I think, because it pops up many times. 1005 joules per kilogram per Kelvin. And CPV, this, again, you probably guessed, it's almost twice as much, 1870 joules per kilogram per Kelvin. Okay? Excellent. Well, very good. Something similar we can do also for the gas constant. I'm not going to go through the entire derivation, but this is what you end up. With. The effective gas constant is RD times 1 plus R over epsilon. Epsilon, I remind you, is RD over RV. And it's about 0.06 over 1 plus R. You could also write this as, if you wanted to do something similar to the above, this would be 1 plus R over epsilon times 1 minus R. Now you know the trick, right? And so this is RD times, 1 plus, collect all the things with an R, 1 over epsilon. How much is 1 over epsilon? Well, epsilon is 0.6, so 1 over 0.6 is, it will be about, 1.5 approximately, minus 1 times R. Terms proportional to R square we're going to ignore. and that's that. Okay. How can you estimate how much is 1 over something? Well, you can use a similar trick to the Taylor expansion here. So 1 over 1 minus x is approximately 1 plus x. And so 0.6, 1 over 0.6 is well, it's actually equal to 1 minus 1 minus 0.4. And so this is approximately equal to 1 plus 0.4. Now, it's not exactly equal, so there will be additional terms, but it's a safe bet that this is actually pretty close to 1.4. So, FYI. I said 1.5, but yeah. So, a trick that you can remember in case you need to estimate things, kind of real quick. And so, yeah, this is 1 plus 0.4, let's say, times R. Now, notice that the way we had defined the potential temperature is also going to change, right? Because we had defined potential temperature in terms of only a dry gas, and so we had ended up with something like theta equals to T P0 over P RCP. Well, these are in CP. You're also going to have to change, and you're going to have to use effective values for these two. Okay. I mean, look, if you need to do really exact calculations, like you're launching the SpaceX to the moon or something, then yeah, by all means use R prime and CP prime, please. But for most applications, you can probably do this and just use, R over CP. You'll have to be mindful of when to use this approximation, but, if you need orders of magnitude and stuff like that, you could probably do it, pretty safely. Okay, now I want to introduce you to a new friend of ours that is called virtual temperature. Well, okay, why do we need virtual temperature? Well, because when we write the ideal gas law, okay, P equals to rho RT. Now things are going to be complicated, right? Because now we have a gas that is composed of different things. So this would be R, we'll have R prime times T. But in some cases, it may actually be convenient to have something like RD, which we can compute, times T prime, okay? So, in other words, it may be convenient to dump all the extra stuff that made the gas constant an effective gas constant into a new definition of a temperature. In other words, the effects of the water vapor that made your gas constant change, dump them into a temperature. Why is that convenient? Well, mathematically, it doesn't change anything because, you have a product of the two quantities. It doesn't matter how you multiply them. But it's kind of easier to think about. It's kind of easier, at least for me, it's kind of easier to visualize changes to a parcel's properties when I think about changes to temperature. Now, mind you, the water vapor is not changing the temperature, okay? But if you write it like that, it's as if the water vapor was, adding water vapor was modifying the temperature of the gas, if you will. And so, in other words, another way that you could put this is that instead of using the temperature of the gas and the new gas constant, you could ask, what is the temperature that a completely dry gas, completely dry air, would have to have in order to have the same density as dry air. Okay? And the answer to that is this T prime, or as is often denoted, TV. This is called the virtual temperature. Okay? And virtual temperature, if you just plug in, remember that R prime was here, R prime was RD 1 plus R over epsilon over 1 plus R. Okay? So TV is simply T. The RDs get simplified. And so virtual temperature is going to be related to the mixing ratio in this way. Okay? With an approximate formula. Like this. Okay? And okay, so it was a little bit more than 0.5, but anyway, the reason why this approximate, so I'm just thinking about the 0.6 here. We gave an estimate here, and we said, well, it'll likely be 0.4, 0.5. The reason why we're a little bit off is that when we use the Taylor expansion, 1 over 1 minus x, x has to be much smaller than 1, and in our case, x was 0.4, which is not a lot smaller than 1. So in order to have a good estimate of the 0.6, we would have had probably to include higher order terms. But again, just to have an order of magnitude, you can use the trick that I taught you earlier. Anyway, enough of that. The virtual temperature. And why is the virtual temperature important? Well, do you remember how we defined, how you defined, or you probably seen buoyancy? Archimedean buoyancy. The story of Archimedes, taking a bath and suddenly he realizes stuff and shouts Eureka and runs out of the bathroom. That story. Well, what Archimedes had realized is that this feels a little redundant at this point in your life for me to remind you of this, but essentially any mass, any body that is immersed in water experiences a force that is proportional to the density, to the difference in density with respect to water. The good old Archimedean buoyancy, you can write it, I think, in terms of, density of the water, difference in densities divided by the density of the water, or whatever liquid you're immersed in. So this is the difference between the density of the body that you're putting in the liquid and the density of the liquid, and this is the density of the liquid. Well, it turns out that if you imagine a parcel of air of density rho in an environment of density rho bar, well, the Archimedean buoyancy of this parcel can also be written in terms of virtual temperature. Differences in virtual temperature between the parcel and the environment divided by the virtual temperature of the environment, which I'm going to denote with a bar. Okay? So, in other words, virtual temperature is a useful quantity because it's something that is very closely related to the buoyancy of the parcel, and that's why it's kind of useful to think in terms of virtual temperature, because if you had thought only in terms of the gas constant and how the gas constant changes, how much can you squeeze out of that? But in this case, having defined a new temperature, and meteorologists love temperatures and introducing new temperatures, you've gained a new way to estimate, in a way, the buoyancy of a parcel, which is always useful. And notice also, as a reflection of the fact that water vapor is lighter than water. Sorry, the water vapor is lighter than dry air. Notice that the virtual temperature is always going to be greater than the temperature because of this term. Okay? So the presence of water vapor by itself is going to make your parcel more buoyant than it was before. Okay? And this is important because particularly in the tropics, this can have big consequences. In the tropics, I don't know if you know, but in the tropics, particularly close to the equator, temperature above the boundary layer, so in, let's say that this is surface of the ocean. Let's say that this is the boundary layer. So this, think of this as, I don't know, cloud top, 2 kilometers. Well, temperatures above the surface and far away from the surface tend to be quite similar zonally. So the temperature here and the temperature here are pretty similar in what is known as the weak temperature gradient approximation. Okay, so temperature variations in the atmosphere are actually pretty small in the tropics, and therefore changes in the amount of water vapor and the humidity of the atmosphere are going to have a big impact on the weather in the tropics. In the mid-latitudes, you can have big gradients of temperatures, and so, whatever. Maybe water vapor is still important, don't get me wrong. But in the tropics, it can actually make a huge difference in terms of what will happen. Okay, well, something similar also holds, similar combinations also hold for other quantities like entropy, for example. We said that entropy was an extensive quantity, right? And so the entropy, suppose you have a mixture of dry air, liquid water, and water vapor. So, you have this box, liquid water, and you have a humid gas above here. The total entropy of this system will be the total entropy of the dry air plus the total entropy of the water vapor plus the entropy of the liquid water, which written in terms of specific entropies, you can separate entropies in mass and specific entropy, and by the definition of mixing ratios, then you get to this simple combination. Okay, the specific entropy of dry air the specific entropy in this system is the sum of the specific entropy of the gas, of the dry air, plus the specific entropy of the vapor and the liquid water. These two weighted by the mixing ratio of the two. Of course, we're assuming in this that the amount of liquid water, is smaller than the amount of the dry air, and the amount of water vapor is smaller than the amount of dry air. Okay, so something similar to the atmosphere that can make these equations possible. The Clausius-Clapeyron equation also can be written in simple form. Remember before we said, well, the differences in the specific entropies are related to differences in specific heat. Well, and those are simply the latent heat. So this is another way of writing the Clausius-Clapeyron equation in that for this specific system. When you use saturation entropy, you can just write it like this. And with that, there's a simpler way of writing moist entropy. I don't want to complicate your life too much. But essentially, using Clausius-Clapeyron equation, we can use this to essentially get rid of SL, right? Because from this, you'd have that SV star minus SL equals 2LV over T, right? And so, sorry, this was an S. This is supposed to be SL. And so, excuse me. Actually, let me rewrite the left-hand term. Okay, now I'm happier. And so SL equals to SV star minus LV over T. Okay. Also, as another definition, RT that we'll use now is RV. We can define a total water mixing ratio as the sum of the mixing ratio plus the liquid water mixing ratio. And if you do that, you end up with a simpler way of writing down the specific entropy. Okay. Okay. And so with some math, finally, you can put everything together with, you can use, the ideal equation of gas, yada, yada, yada. And at the end of the day, you can do some transformation and you end up with this new, function, okay, this new variable. This variable is called equivalent potential temperature. Now, I don't want you to remember all these steps that we went through, okay? How we started from entropy, and we arrived at the end with these different steps. We arrived to the equivalent potential temperature. It doesn't matter. Don't worry. You don't have to remember this. The point of all this was that when you start with dry entropy, you get to the definition of the potential temperature. And if you remember, there was something like S of the dry air parcel was related to CPD, logarithm of theta. Okay. With the, actually, I prefer to use this ds. With a more complicated mixture where you have water vapor and dry air, things will be complicated. If you remember last lecture, we said this would not be able to use anymore. We have to make it a bit more complicated. Well, this is how complicated it's going to get. And it looks quite complicated. But the point is, there's a way to define the extension of dry entropy to moist entropy that would lead you to the equivalent of potential temperature for moist parcels. That is called equivalent potential temperature. Okay. Okay. Another quantity that is kind of useful is called moist static energy. Okay. And this quantity is similar in a way to equivalent potential temperature, except that it's really not the same. But it's sometimes it's used in similar ways. The moist static energy is defined starting from the first law, the first principle of thermodynamics, and in particular imagining an adiabatic process. Okay, so remember, changes in internal energy changes are given by exchanges of heat plus work. Okay. Now, for adiabatic processes, this would go to 0. Okay, and you can write this in. You can write this in. Can write this. Sorry, I'm getting lost. You can this becomes essentially the point I'm trying to get at is that you can go from internal energy, you can go to enthalpy, and you'll have infinitesimal changes in enthalpy equal to changes in V dP. Okay. When there's no exchanges of heat. That was the point I was trying to get to. And when that happens, then you can write changes in enthalpy as the sum of changes due to dry air, water vapor, and liquid water. And notice that now the quantities that come into play are specific heat capacities at constant pressure, except for the liquid water, for which it's just the heat capacity. It doesn't matter, constant pressure, constant volume for the liquids. And and that's because we're using the enthalpy here, okay? And so that would just be the sum of the three contributions weighted by the mixing ratios, okay? Something similar to what we've done. And the specific volume is exactly, this was enthalpy volume dP. This is d infinitesimal changes. This is bad because I'm going to also use this. Infinitesimal changes in specific Gibbs energy, which I will denote the lowercase. I'll just do it with a chi, specific volume in dP, and that's how the two terms are computed. If you remember a few classes ago, we had talked about Kirchhoff's equations that told us how latent heat changes with temperature and how that depended on when you have phase transitions and how that depended on specific heat capacities at constant pressure. Okay, and so we can plug that in, and if you substitute it in, then you can write this simple equation. This remains kind of unchanged. You can plug this in here, okay? And you have a term that contains now CPD and CL. Okay, CPV is kind of being taken out by DLV. And plus these infinitesimal changes in D and V. Integrate this, and essentially you obtain a new function. And in order to go from here to here, you'll also have to use another approximation that is typically denoted or called hydrostatic approximation, that says that infinitesimal changes in pressure are equal to minus rho g. G is the gravitational constant, times changes in height. Okay, so you substitute that, plug it back in, and you have this function. This function is known as the Mystatic energy. This is sometimes we approximate it because, life is short, and RT is a lot smaller than 1, and so you can approximate this with CPD T plus LVR plus GZ. Why are we getting rid of this and not this? Well, because this is 1 plus something, and this is a lot smaller than this. But this is actually multiplied by a really, really big number. So it's not guaranteed that this is small, and it actually isn't normally. Keep in mind that this is order 1,000, and this is order 1,000,000. LV is about 2.56 10 to the 6th. I want to say joules per Kelvin. Per kilogram, not per Kelvin, per kilogram. And these are joules per kilogram per Kelvin. So why are these two variables, theta E and H, why are they important? Well, because these quantities are actually conserved under adiabatic transformations. You could go all the way back. If you start from here, you can go all the way back and find that dq is 0. So in adiabatic transformations, H is conserved. And having conserved variables, trust me, is always a good thing. And same for theta E. Theta E will be a bit harder to see. But this also is conserved under adiabatic transformations. And so suppose that you have a parcel of air, for example, that is going down. Let's say that you have a thunderstorm, right? Say this is a thunderstorm and it's kind of raining, and you have a parcel of air that is inside of the thunderstorm and is traveling down, is what we call a downdraft. Okay. Now, what happens in a downdraft? Well, in a downdraft, the parcel of air is typically surrounded by liquid water, and the liquid water, more often than not, is in a so-called unsaturated or subsaturated environment, meaning that the liquid water is exposed to air that is not saturated. You're outside of the cloud. So when that happens, some of the liquid water will eventually evaporate. Okay, that's kind of expected when you're not at saturation. What happens when you're evaporating water? Well, when you're evaporating water, you're paying essentially, and you're paying in energy, and the temperature of the parcel in the downdraft will in principle decrease. Okay. One might ask you, why, how much is the temperature of the parcel decreasing? Well, who knows, right? Like, how can you determine that? Well, one way to determine that is that if you're going down in a downdraft, this is an adiabatic process because there's no exchange. Nothing else is going on. It's not like the parcel is condensing and losing mass, so nothing is quite happening. The hydrostatic approximation is typically a good enough approximation. It's not like we're considering tornadoes or hurricanes where you might have shock waves and sound waves and weird stuff going on that could compromise the simple equation. So we can use this. And so the parcel at point A, parcel at point B, so the parcel will evaporate a little bit. H, Mystatic energy at point A, must equal Mystatic energy at point B. But that you have a way to measure, because now what this says is that CPD delta T, where delta T is TB minus TA, plus LV delta R plus G delta Z equal 0. Assume, for simplicity, that delta Z is 0. So let's assume that actually A and B are at the same level. The parcel is not moving, it's just evaporating. How much is temperature changing? Well, temperature is changing. Let me write it here. I'm going to just make some space. Delta T is going to be equal to minus L over CPD delta R. How much is this stuff? Well, this is 2.5 10 to the 6 joules per Kelvin. This is 1,000 joules per Kelvin per kilogram. So this over this is about 2,500. And delta R, how much is it? Well, let's say that delta R, you're evaporating 1 gram per kilogram. So it's 10 to the minus 3. Plug everything together and you have that delta T is minus 2.5 approximately Kelvin. Okay, so without knowing anything else, just because you knew that Mystatic energy was going to be conserved, you can have a very simple calculation just because Mystatic energy was conserved. One big caveat was that, there were some approximations like the hydrostatic approximation, which is not always true, hurricanes and such. And also, Mystatic energy is not conserved under mixing. And so if you're mixing this parcel with other parcels that, in the surroundings, MSE will not be conserved anymore. But by and large, this could be a good approximation. In summary, this is why we care so much about Mystatic energy equivalent potential temperature enjoys similar properties. There are approximate formulations of equivalent potential temperature that makes it a little bit more manageable. But this is also a variable that is conserved under adiabatic processes. And so you can use it, and it can be useful for many different applications. Okay, I think this is pretty much all I had to say. So just review the formula. It's not so important how you derive the formula, but just keep in mind things change when you include water vapor now in your mixture. And today we saw how things change when we start including water vapor. If I'm not mistaken, this marks the end of the thermodynamics part. I'll double check, but this should mark the end of the thermodynamical part. And from next time, we will start. I'm actually scrambling to look for a syllabus. Yes. Looking at the calendar, our thermodynamic part is over, and now we're introduced the water vapor. Next time, we will talk about what happens when temperatures cool down a little bit too much, or you've added a bit too much water vapor, and the air starts to get rid of the water vapor by a process known as condensation. And we'll start the part on microphysics. As usual, let me know all your questions, which I'm sure will be many. And if you're confused about any of the things that I talked about. Otherwise, I will see you for the next lecture. Thank you very much for listening.